In this question, we're given that we have this 4 kilogram block and a 2 Newton force is applied to it at a downward angle theta as the block moves towards the right through a 1 meter distance on a frictionless floor. We want to find an expression for the speed, the final speed, at the end of the 1 meter distance if the block's initial velocity is 0 first, and if the block's velocity was 1 meters per second next. So let's start by thinking how we can deduce the speed from a given force and mass and distance. So trivially we would think of studying the work energy theorem. So we know that the change in kinetic energy is equal to the work done by the forces. So delta K is equal to the work done. And here if we look at our displacement, which is horizontal, this makes us know that we only look at the forces which contribute to this horizontal displacement. So forces with x components will be considered in the work done. And if we look in our example, the weight and the normal are vertical, whereas the applied force is oblique and will have both x and y components. So we consider only this applied force to contribute to the work done. And so we can substitute our equation to be K final minus K initial equals to the work done by this applied force. Now the final kinetic energy has an expression of half mv squared. The initial kinetic energy is just 0 since the initial is 0. And the work done by the applied force is equal to the force itself times the distance times cosine theta, where theta is the angle that the force makes with the horizontal, because this is the direction of the displacement. So if we rearrange this to get an expression for the speed, we will get 2 fd over m times cosine theta. We are requested to find Vf as an expression in terms of theta, so we need to remove the rest of the unknowns or the rest of the terms that we have. We know that the force is 2 newtons, the distance covered is 1 meters, and the mass is 4 kilograms times cosine theta, and then our final expression for the speed is going to be, by the way, this is squared. So this is going to give us Vf squared equals cosine theta. So Vf equals radical cosine theta. This is our expression for the final speed if the initial speed is 0. Now, if the initial speed is 1 meters per second, then the initial kinetic energy will not cancel out. Our expression will be Kf minus Ki equals the work done by the force. And this leads to an extra term, including this initial speed, which is 1 meters per second. And this will be equal to fd cosine theta. Now if we rearrange this, this will give us v final squared to be equal to 2 over m into half mv initial squared plus fd cosine theta, and this will give us v initial squared plus fd times 2 over m times cosine theta, and this is equal to 1 plus cosine theta. So v final will be radical 1 plus cosine theta. In part C, we are told that we want to study v final again, but the situation is similar to part B, that the block is moving at 1 meters per second to the right. So the initial speed is 1 meters per second, but now the 2 Newton force is directed downwards to the left, so the direction of the force is different. We can see that if our object is moving to the right and our force has this new direction, it's actually going to be resisting the motion. So F here does a resistive work. Since its x component is actually in the negative direction, as you see here, it's opposite to the direction of the displacement. So this is Fx versus d, they are opposite. So Fx is opposing the displacement now. So it will do a negative work. Now, how do we see this in our expression? We know that we have again Kf minus Ki equals the work done by the force. We will see that everything remains the same except for the work done, and the difference now is that the angle that the force makes with respect to the displacement is now not equal to theta, but it's equal to this whole angle here, which is actually 180 minus theta. Which is basically minus cosine theta. So we can write this as minus Fd cosine theta. Now again, if we rearrange for V final, we will do a similar calculation to part B, but we will end up with this expression 1 minus cosine theta with a radical. So this is our expression for V final. So we got here three expressions basically for different situations: a situation where we have no initial speed, a situation where we have an initial speed of value 1 meters per second, and an expression for V final with the direction of the force being opposing the direction of motion. Now, a very interesting thing to study here is to plot these expressions. So we can plot V final versus theta. So for different angles, what would V final look like? Now we know that V final has these three expressions for the three situations, but they are all in terms of cosine theta, right? So plotting them will give us sinusoidal curves. Let's say that we want to find the plots with theta equal to 0 all the way to 90. So we're interested just in this region. So to plot this with our y-axis containing V final and our x-axis showing theta itself, we said theta will go all the way from 0 to pi over 2 only. Now, if we look at our expressions, for our first expression, Vf equals radical cosine theta. We see that as theta is increasing, the force will be giving less and less of a positive acceleration, and so it will contribute less and less and do less work. And if we want to plot this, let's say we start with theta equals 0. So cosine 0 is going to be equal to 1. So at theta equals 0, V final will be radical 1, which is 1. And if we look for the value when theta is equal to 90, this is cosine 90, which is equal to 0. So Vf will be 0 when theta is equal to pi over 2. And this is a sinusoidal curve, so we will expect it to have this shape. Now, for our second expression, for theta equals 0, V final will be radical 2, which is about 1.4. So we can plot our second graph starting from the point 1.4 here. And for theta equal to 90, we will see that v final will be equal to 1. So our graph at pi over 2 will end up here. And again, this also will be a sinusoidal curve. So we draw a curve here. Now for the third expression, we see that for theta equals 0, v final will be 0 because it's radical 1 minus 1. And for theta equal 90, v final is going to be equal to 1. So if we plot this, we will be starting from 0, 0 all the way to 1. This is our graph. So this is for the third expression, 1 minus cosine theta. This one was our first expression, which is radical cosine theta. And here we had our second expression, which is radical 1 plus cosine theta.